I'm going to go ahead and pick up where we were yesterday, and I believe we finished with E. What E looks like is, if you recall, we had this graph that looks like this. My sine wave is going to go like this to 2 pi. My cosine wave is going to look like this. And right here, this is the point in which they intersect, and that's at pi over 4. So now I'm going to integrate between 0 and pi over 4. Now, this is the region in which I'm integrating, and I can see that my cosine wave is the one that's on the top when I do this. Now, this is going to be a washer, because what happens is I'm going to have these two shapes. Here's where my sine wave is. Here's where my cosine, actually, let me do that in red. Here's where my cosine wave is. And I can see the radius for the cosine wave at any given time, that is the red, will be the cosine of x, is going to be my radius. And then in black at any given time, that is the sine of x, is going to be that radius. And what I want is I want the subtraction of both of those. So what I'm doing is I am finding the area of the cosine x minus the area of the sine x. And we know that the area of a circle, so the area of a circle is equal to pi r squared. So when I do this, I'm going to have pi. My radius, my outer radius is cosine, so that's going to be cosine x, the quantity squared. And then minus my inner radius, which is going to be the sine, so that is minus the sine x, the quantity squared, dx. Now, when I do this, I'm going to have pi, don't forget the pi, I like to forget pi, pi over 4, and I'm going to have the cosine of x squared minus the sine of x squared dx. And then if you remember right, I sent you all out a trig cheat sheet that you would have had in pre-calculus 2. And we have a formula in pre-calculus 2 that if I have the cosine squared x minus the sine squared x, this is equal to the cosine of 2x. It's the double angle formula. So that tells me that this is equal to pi, and the integration from 0 to pi over 4 of the cosine of 2x dx, because this can be replaced with just the cosine of 2x. Now the antiderivative of the cosine of 2x is going to be the sine of 2x. However, if I were to do d dx of the sine of 2x, I would get the cosine of 2x, but then I'd also have this multiplier of 2. This is missing that multiplier of 2, so this is just going to be pi from 0 to pi over 4 of, don't forget the multiplier 1/4, so just want to go right to the integration here. Sorry about that. Do the integration of pi, don't forget that pi, of 1/2 the sine of 2x integrated, that should be an integrated from 0 to pi over 4. So then all I have to do is this is going to be equal to pi, don't forget the pi, I always forget the pi, of 1/2 the sine of 2 times pi over 4 minus 1/2 the sine of 2 times 0. So this is going to be equal to pi, don't forget that pi, 1/2. Well, the sine of 2 times pi over 4 is the same thing as the sine of pi over 2, which happens to be 1. So this is going to be 1/2 multiplied by 1 minus the sine of 0 is 0. So minus 0. So my final answer is just pi over 2. And then because this is a volume, I would have units cubed on this. this example here wasn't just a solid in which it was a solid circle. So it wasn't like a cylinder like we had before it and the cross-sectional area was a solid. Our cross-sectional area, except for our very first disc, was actually a donut shape. So we're going to do what we call the washer method, or by slicing. So we are going to have to pay attention to who is on the top function, who is on the bottom function. Or if we are going with respect to the y, the first function as I read it to the second, so the left function and then the right function. So if I'm integrating with respect to x, I have to pay attention to which function is on the top and which function is on the bottom. If I'm doing it with respect to y, then I have to pay attention to who is on the left and who is on the right. And all that does is, when we're doing the washer method, as you'll see, that our cross-sectional areas are donuts instead of a solid circle. So we have this donut, we have a cavity in it, and for this, what we do is we do the pi. This is going to be the f of x squared minus the g of x squared, because what we're doing is we're saying if I find the area of a circle and I subtract off the area of the other circle, so if I have this shape, so I have this entire area here. Let me do it this way. Let me draw it a little bit better. So let me do one in a different color. So area of this circle. So here's this circle. If I subtract off this circle, then what I'm going to have is the donut that I need. So what I do is I do the radius of this one squared, so radius squared, and then we do the radius of this one squared, and if we have the pi attached to both of them, we notice that the pi is common, so we can factor it out. And then it'll be the function on the top squared, which is your radius, minus the function on the bottom squared, which is your radius. And then what you'll have is that, that shape, which is the donut. If we are doing it with respect to y, then still the pi is the same. This is your rightmost, and this is your leftmost. So we'll take the right squared minus the left squared of its respect to y, and we'll take the x squared, or the top squared minus the bottom squared of its respect to x. So the first thing I have to do is I always have to draw the shape, and then I have to figure out with respect to which way I'm going. So of all of these, which one would you like me to do? A, B, C, or D? A, B, C, or D? So as we take a look at D, the first thing I'm going to do is figure out what this graph looks like. Now, normally when I have E, it's usually to the x, and in this case it's not with respect to the x, it's respect to the y. So what I do when I draw it, if I have to hand draw it with respect to the y, is I just turn my iPad so that it looks like I would expect it to look in terms of x and y. So here's y and here's x. So if I have to draw this with respect to y, then I'm just going to turn my iPad so that my positive x is up. So I'm first going to draw this part, and this part looks like this, give or take. So that is x is equal to y squared. My second part is I'm going to draw e to the 2y. Well, e to the 2y is going to start out here, and it's going to look something like that. So that is e to the 2y. Okay? And they're telling us where I am going to rotate between. So I'm going to cut it at y equals 0. That's this part. and I'm going to cut it at the natural log of 2. So y equals the natural log of 2. So somewhere about here is where I'm going to cut it. So the natural log of 2. So this is the region in which I'm going to be doing the rotation on. And you can see that my e to the 2y is the one that is the rightmost graph. Now, so when I do this integration, I'm going to go from 0 to the natural log of 2. I'm going to have pi as a multiplier. My most right one is e to the 2y squared minus the left one, which is y squared, and then dy. And now I'm going to integrate this. So this is going to be pi from 0 to the natural log of 2 of e to the 4y minus, that should be y squared squared, so y to the 4th dy. And now I do my regular integration. And so, I'm trying to make sure I can give everyone the space to see all of this. And so this is going to give me 1/4 e to the 4y. Because if I do the derivative of e to the 4y, it should have had 4 as a multiplier. I don't see that there. So I'm going to do that. And then, of course, I forgot my pi again. I shouldn't, because pi is delicious. So pi, and then 1/4 e to the 4y. And then I'm going to do my regular rules for powers. So this is going to be minus y to the 5th divided by 5, integrated from 0 to the natural log of 2. So going ahead and putting in the natural log of 2 and 0. So I have 1/4 e to the 4, the natural log of 2, minus 0, or minus the natural log of 2 cubed. Erase that. So minus the natural log of 2 raised to the 5th power divided by 5, minus 1/4 e to the 0 minus 0. So this is 1/4. Now, e to the 4, the natural log of 2, is e to the natural log of 2 to the 4th, which is equal to 2 to the 4th. And I'm using some the rules for logs. The rule I'm using, which says if I have b raised to actually, let me put that in the right place. The rule that I'm using to do from here to here is if I have b raised to the log base to b of x, it equals x. So that's the rule I'm using there. The rule that I'm using here, which is the log base b of x raised to the p, is p the log base b of x. So in other words, I'm just reversing that. That multiplier up front becomes a power on the 2. So that's why I was able to just say that this is just going to be down here. Let's go back to where I was. That this is just going to be 2 to the 4th. So 2 to the 4th. And then minus the natural log of 2 raised to the 5th divided by 5. And then this is going to be e to the 0 is 1, so minus 1/4. All right. So I can actually put that in web work just like it is. I'm just going to kind of clean it up just a little bit. We're going to do the decimal equivalent. 2 to the 4th is 16 divided by 4, so it's 4 minus 1/4 minus the natural log of 2, the quantity squared, divided by 5. So I might write this as 3.75 minus the natural log of 2, the quantity squared, divided by 5. Or I may just put this in my calculator, and if I put it in my calculator, I am going to have to write it out to about 5 decimal places for web work. Is there any question on anything I did there before I have you go back in? Oh, and I forgot the pie. Pie is delicious, and I keep forgetting it. Damn it. So there's pie here. There's always pie. Thank you for that. I am just forgetting that pie every time, and pie is delicious. All right. Any questions besides the fact that I dropped my pie? Don't drop your pie. Any questions besides that? Then are you okay with me moving, or do you need me to stay here for a minute so you have the opportunity to write this all down? I just need to know if I can move up so you can see the ones that I want you to work on, or if, okay, I'll stay for a couple. Now you'll notice I added some comments on the notes here. So for B, when it says I need to go around the y-axis, then I need to solve for x equals. And if I'm going around the x-axis for this particular method, you need to solve for y equals. For the first one, it's pretty straightforward. I just have two lines. They are running parallel to each other. And then it's just a matter of knowing which one is above the other. And in this case, the x plus 6 is above the x plus 2. Because it has an intercept of 2 and the other one has an intercept of 6, but they have the same slope, the x plus 6 is above. So using this method, it's going to be pi, and then it's x plus 6 squared minus, and then I have x plus 2 squared. Don't forget the pi, because I seem to always forget it. You all need to not forget the pi. When you do this integration, you have one of two ways of doing this. You can go ahead and distribute the integration and write it as pi, and 0 to 5 of x plus 6, the quantity squared dx, minus integration pi, don't forget that pi, 0 to 5 of x plus 2, the quantity squared dx. And then this will allow you to use u substitution if you're inclined. Now if you don't want to do u substitution and you don't want to break it apart, you're really good at multiplying stuff out correctly, then you can do it this way, from 0 to 5. You multiply out x plus 6, the quantity squared, is going to give you x squared plus 12x plus 36, minus, and then if you multiply out the x plus 2 squared correctly, you get x squared plus 4x plus 4, and then dx, and then you can combine up like terms. So how you approach this one is totally up to you. I probably would break it apart and then do u substitution, but if you don't want to break it apart, you're like, I'm really good at multiplying stuff out, cool, you can do that. For this one, if I were to set this up, first thing I would do is I'd draw the graphs of the two before I solve for x. So I'm going to draw the x plus 2. Well, x plus 2 is going to look something like this. This is y is equal to x plus 2. My other one is 2x minus 1. So 2x minus 1 is going to look something like that. So 2x minus 1, that's y equals. The only reason I'm going to set it up that way is because I'm pretty comfortable with doing the lines without needing to solve for y first. So I can see which one is on the top. I know that as I read from left to right, this one here is the one that I'm going to do first. But because I'm doing it around the y-axis, I'm doing it in this direction, I have to have x equals. So I'm going to have to take this and solve for x. So y plus 1 is equal to 2x. That means y plus 1 divided by 2 is equal to x. So when I do my integration here, I am going to integrate from x is equal to 0. So from x is equal to 0 is here. So the region I'm going to be integrating is this. I'm going to do from y equals 0. Actually, I'm going to do all the way down here. It's going to go all the way down to here. So when y equals negative 1, because all I'm restricted is when x is equal to 0. So I do have to take that little piece. And when I do that rotation, it's going to have it rotated over there. So it's going to have it this V shape is what it's going to look like when it's rotated around. So it goes from negative 1, and then I have to figure out this y value in which they cross. So I'd have to do my integration from negative 1 to whatever that y value when they cross. So if I set these equal to each other and solve, I'm going to have x plus 2 is equal to 2x minus 1. I'm trying to figure out the x value. So I'm going to subtract x from both sides. I'm going to add 2. So when x is equal to 3, that's where they're going to cross, but I need the y value. So I'm going to put that into one of the two functions. I'll probably put it in this one. So I have 3 plus 2. So when y is equal to 5, that is my upper limit. So from -1 to 5. Now I know I'm going kind of fast and I apologize. I just want to finish the setup before we finish for today, and I'm already over time. So I solve for y on this second one here, and so y minus 2 is equal to x, or solve for x. And so when I set this up, it will be my upper one, y plus 2 squared over 2 squared. And then it's going to be minus my y minus 2 squared. Don't forget your pi. And then let me erase some of this stuff. dy. So that's how that one's going to be set up. Now, I'm just going to erase this so I can have that space. I did do the drawing so you didn't have to go out into Desmos to figure out what the graphs look like. Now, I'm doing this with respect to the x-axis, so I'm going to revolve around the x-axis. That means I need to have it y equals. So if I take the blue one and I have x cubed, and I wrote a squared, x squared is equal to y cubed, then this is going to be the cube root of x squared is equal to y. Now that is the one that's on top because I'm doing it with respect to the x-axis, and so it is going to be the top function. And then if I solve for the other one with y, I get positive and negative x cubed is equal to y. But I can see from my graph, since I am revolving around the x-axis, it's going to make no sense for me to have the negative region of this. So this negative region right here, as I'm drawing it really big and heavy, I'm not going to need that part of it. So that means I'm just going to take the positive. So I'm just going to have the positive of it. When I integrate it, I can see with my integration, don't forget your pi, I'm going to start at 0. I have to figure out what this crossing point is. But I do know my upper one is going to be the cube root of x squared squared minus, let me erase this, minus my lower one, which is the square root of x cubed squared with respect to x, so dx. So all I have to do now is I have to set these two equal to figure out where they cross. So the cube root of x squared is equal to the square root of x cubed. And without doing any work, I can tell you the only time that happens is when we're working with a number 1. That's the only time that's going to happen. So my upper limit has to be 1. Is there any questions on any of these before we finish? And thank you for letting me go over by 5 minutes. Is there any question on these?